Okay, 1-6 was the last of the sections coming directly from that textbook. So this was our inverses. We talked about how to figure out if something's an inverse or 1-to-1 because those mean the same thing. From points, we said the y couldn't repeat without a different x. And then from a graph, we used the horizontal line test. And then from the equation, the x cannot be raised to an even power or an absolute value. So first of all, these already say, like, does the function have an inverse? So it's already assumed that these are functions. Remember that if it had said first, is it a function, that you'd have to test for that first. So it would say, is it a function? You'd use your vertical line test. And then if it is a function, is it 1-to-1 or does it have an inverse? Then you would check for that. Make sure you're reading instructions on stuff like that because you would hate to like dive right in and give an answer and then it not even be a function to begin with. So for number 1, does it have an inverse? No. A horizontal line would literally hit every point in that. So this is no. 2, does it have an inverse? No. If I drew a horizontal line through it, it's going to hit it more than once. 3, does it have an inverse? Yes. And if I wanted to find it, I would plot some points and then I would take and switch them to make my inverse. 4, does it have an inverse? No, because the x is raised to the even power. So there's a lot of explaining that needs to be done in words as far as AP questions go. So make sure you would also be able to explain that. And then 5, yes or no? Yes. Okay. 6 says find the actual inverse of the function. So step 1, replace the f of x with y. Step 2, switch your x and your y. Step 3 is solve for your new y. So I'm going to subtract the 5. I'd get x minus 5 equals 2y. Divide by 2. And y equals x minus 5 over 2. And then I cannot leave it like that. I have to change that y to f negative 1 of x. You can leave it as x minus 5 over 2, or you could make it 1/2 x minus 5/2, or minus 2.5 if you had to graph these. So if it said to graph the original and its inverse, then you'd have to split it up like that. But as far as finding it, either of those answers would work. Questions? So not changing that f to f of x or the y back to f negative 1 of x is a way to lose silly points. Like, don't make that mistake. You have to change it because that is no longer the original function. We changed it. All right. Questions on inverses before we move into change in tandem? Okay. So this is AP topic 1-1. Remember, there's like 14 topics in the first unit, okay? We're going to divide them, like, we're going to do, the plan right now is 1-6, 1-1, and 1-2 on a quiz for Friday. And then we'll move into the rest of it, and you'll test after that. But midway through, actually, no, a third the way through unit 1. So this homework is the first that's going to come in 2 parts. Part of it is going to be a PDF practice, and then part of it is coming from AP Classroom. If I can pull in from WebAssign, I will continue to do so, but this topic is not in your textbook. So that's why we're going to supplement it a different way. All right, so a function, and we talked about this in terms of like general, what's a function? The definition of a function is a mathematical relationship that maps out a set of input values to a set of output values, such that each input value is mapped to exactly one output value. So notice the change in language from your pre-calc textbook to the AP content. Instead of saying X values and Y values, we're using words like input and output, okay? That's really the only difference here. The input values are your X values. The output values are your Y values. When you are asked to explain something, you have to use those terms. So if it said, why is this not a function, you would say either one input value matches more than one output value or something like that. You can't just say X and Y's. On the graph, the X values are the input values. These are also called the independent values. So when you're looking which one's independent and which one's dependent, the X is the independent and the Y is the dependent. If you think about it, independent is what you plug into your equation, so it could be anything. You pick those from whatever. but your dependent is what happens when you plug those in. So the X is your independent and the Y's are your dependent. Vary in tandem. So the variables in a function will vary in tandem according to the function rule. And the rule can be expressed in 4 different ways: verbally, analytically, graphically, or numerically. Verbally is something like, as the input values increase, the output values increase. Okay? It's not always increase, increase. It could be increase, decrease. It could be decrease, increase, or decrease, decrease. That's just the way we would describe it in words. So this is the same as saying, as the X values increase, the Y values increase. But we have to use words like input and output. Analytically is like, what does that mean? Well, for all the values of A and B in this specific interval, A and B, if A increases, then B increases. So our graphs can increase, decrease, they can rise, they can fall, that kind of thing. And you'd have to be able to analyze them on an interval, which you'll see that in a little bit. It'll say what's happening from this number to this number. Graphically is pretty obvious. It's a graph, okay? So if those values on this graph, specifically, it's time and speed. So our input values are our time. That would be our independent value. And the speed is the output value or the dependent variable. So in this case, we would say as time increases, the speed increases, okay? And then numerically would be literally a set of data. So if I'm looking at this data, if you notice the top, which is your X values, those would be your input values. The bottom is your output values. What's happening to the bottom values? They're getting bigger. So I would say as the X value, the input value is increasing, the output value is also increasing, okay? That's how you would read these kinds of things. Example 1, and there's a typo, but my PowerPoint on my Mac is not working, so I cannot fix it. You're going to change this to 5. That's why I hadn't posted them yet, and I forgot, but it's not working. Okay. State whether the function is increasing or decreasing on the given interval, and then justify your answer. So for A, from interval 1 to 5, what's happening to these output values? They are decreasing. And we would say something like justifying your answer as the input values are increasing, the output values are decreasing. God bless you. Now, they could have given you a smaller interval. Let's say that those values, because they don't always have to go in one direction. Let's say they went up and came back down again. It could ask you for just one part of that. From this interval to this interval, what's happening? So those answers might change depending on the interval of the graph or of the table. In this case, they were decreasing the entire time. But they could also restrict your interval to be different so that different answers would be there. B is from 2 to 9. I know it looks like a Q, but that's a 9. So from 2 to 9, what's happening to this graph? It's increasing. So this time as my input values are increasing, the output values are decreasing. I'm sorry, are increasing. And C is from 5 to 12. What's happening to those values? They're decreasing. So as input values are increasing, output values are decreasing. And then kind of like we did back with scatter plots, if it actually gave you terms there, if it was time and distance or whatever it is that's there, you would be more specific. As time increases, the distance, whatever it is, okay? You would be specific to it. Questions on those? All right, concavity is something completely new, okay? So this is not concave as in a polygon, okay? If we remember that from like geometry. There is two different types of concavity, concave up and concave down. And concave up is the rate of change increasing. This is not saying your graph is increasing. It's saying the rate of change is increasing. So this is like something like a car is speeding up, okay? So as you start to accelerate, maybe you're going a little bit slow, but then as you continue, it's going faster. That would be your rate of change increasing, okay? And that would be concave up. So you're going to have to read this two different ways. One is literally, it will tell you something is increasing or something is decreasing, and you have to know that that means concave up or concave down. And then the other is from a graph, which I'll show you in a minute. Concave down, the rate of change is decreasing. So maybe you're slowing down, okay? Maybe your speed is still increasing, but you're going at a slower increase, okay? So in the beginning, you're flying, but then you ease up. You're still going fast, so you're still increasing your speed, but you are going less acceleration than you were before. Does that make sense? So it doesn't mean you're coming back down necessarily. It just means that you're slowing it down, okay? So your rate of change is decreasing. And it says it here in these little graphs. It says for equal changes in the input, the corresponding change in the output is increasing. That causes concave up. So one way to look at this, and to me this was more confusing than I'm about to show you, but one way to look at this is if you have equal spacing, the problem is you don't always have equal spacing. If you have equal intervals of your x values, so notice all of these are the same, okay? And then you compare the corresponding y change. If that y is changing more, so the actual vertical shift is higher, then it's increasing, which is concave up. If you have the intervals, I think this is easy to see. If your steps are getting taller, okay, then it's concave up. But you're not always going to have those equal intervals. You're going to see that in a second. If the change is decreasing, so notice that the x value or x change is still equal. Now the y value or the vertical change is getting smaller. This is concave down. So if the change is decreasing, concave down. And again, you're going to see this in words and then you're going to see this in graphs. I'm going to show you a trick with the graph. But in words, it looks like this. The directions underneath says the table describes rate of change of a function for selected intervals of x. The function f is defined for -1 is less than or equal to x, which is less than or equal to 3. On which of the following intervals is the graph of f? A, concave up, B, concave down. So go back up to your chart, okay? Notice it says rate of change. This is not just saying my graph is increasing, meaning it's going up and coming back down. This is the actual rate of change. So negative and constant and positive and constant actually have no bearing on concave up or concave down, okay? What we're looking for are the words increasing and decreasing. If the rate of change is increasing, what is it doing? Concave up. And so this is from 0 is less than x, which is less than 1. Remember all that practice we did with interval notation? Go back to inequalities, okay? So we're going to use inequalities here instead of interval notation. Not that you'll never see it again, but for these, we go back to our inequality notation. All right, and then what is it when it's concave down? Decreasing. So that would be from 2 is less than x, which is less than 3. So in between 2 and 3. I feel like the chart's pretty straightforward. You're looking for the words increasing and decreasing if it's the rate of change, which is what it's going to be given on the left-hand side. It'll be the rate of change, not the actual values. Okay, now we're going to read a graph. This 3 of these things we have done before. The zeros of the function, how do I know it's a 0? Crosses the x-axis. And if I asked you to give me the zeros of a function, how would you write them? The x values. So you will literally write x equals whatever. X equals whatever for as many zeros as there are. If I wanted the x-intercepts, what do they look like? They're coordinate point form. So it is still where it crosses the x-axis, but these would be, x-intercepts would be a number, comma, 0. These would be in coordinate point form. God bless you. And then a y-intercept happens where? Where it crosses the y-axis. And I know I told you to put it in coordinate point form. AP doesn't want it in coordinate point form. It wants it to say y equals. So you will put y equals, almost like you do your zeros with your x equals. Increasing and decreasing behavior, we put in what notation? Before. Interval notation, but we're not going to do that anymore. Because why? Because why would we do something we already did? We're going to change it. Yeah. So on increasing and decreasing behavior, which values do you look at, the x or the y? X. So if it's increasing, let's say my function is doing this, okay? And this is 0 and this is 4. We would say it is increasing from 0 is less than x, which is less than 4. That's how it's going to look. And then if it came back down, we'll say this is 6, then it would be decreasing from 4 is less than x, which is less than 6.
When you're writing like the increasing and decreasing, why don't you put greater than and equal to?
Just like we can't use the brackets, that point technically is shared by both, and a point can't be increasing. Yeah, so a point itself can't be increasing or decreasing. It will get the not or equal to. Yeah, good question. Okay, and then concavity. So we're going to do concave up and concave down, okay? From a graph that does, like, I don't know, like snakes. Like, let's say it goes up, down, up again. You're not going to have those same intervals drawn out. It's in my opinion, it's harder to, like, make sure that they're precisely the same width and then figure out your vertical change. The easiest way to see concave up and down for me from a graph is a concave up makes a U, like a parabola pointing up, and concave down, so up, does this, and down does this. So as you go through your graph, the first shape does this, and that's where it cuts. That part of my graph would be concave down. And then from that point to that point, that part of my graph would be concave up. They won't always be equal portions. That's why it gets a little bit trickier. And to me, I think that's easy. I think if you can see the spot of the curve, okay, then you should be able to distinguish it from your graph. Questions so far? All right, so this puts it all together. Use the graph of f below to answer the following questions. When is the graph concave up? When is the graph concave down? Find the zeros, find the y-intercept. When is it increasing and when is it decreasing? Okay, so let's start with the concave up and down, okay? Notice that this shape on the left kind of flows into the right. You have to stop your curve the moment it starts to change direction. So that first U would look like that, and that part of my graph would be what? Concave up or concave down? Up. So if I was to label it, notice it doesn't give values. It's giving you letters. It's going from G to I. So concave up would be, it's less than, because this arrow is going to keep going. So it's going to go from negative infinity to I, which means anywhere x is less than I. Say that again. Because this starts to change to that direction. Like you see, it starts to peel off. That's where that concave cavity is going to change. The rate of change there slows down, if you want to look at it that way. Okay, then it starts here. Oops, let me highlight. Comes here, and my curve goes like this before it starts to take off on that second part. That would be what? Concave down. Now this time I've got a start and an end. So I is less than X, which is less than K. And then it comes back up again. So it'd be where it's greater than K. Just like our graphs from before, we assume the ends are cut off would be arrows, and it would continue on in that pattern. All right, on the graph, where's the little point that's the y-intercept? A. So we would say y equals A. Yep.
I think you skipped it.
I sure did. Thank you. Concave up. X greater than K. Okay. Zeros happen where? At G and M. So I do X equals G and X equals M. So we technically don't use the term like points of inflection in pre-calc speak, but the points of inflection are where my concavity changes direction, okay? Where it changes from going up and down, which was here at I, here at K. That's called a point of inflection. For increasing and decreasing, we look for what values? Where is it that they changed from increasing to decreasing and decreasing to increasing? We did it with our graphs before. What points determine where the increasing and decreasing start and stop? The relative max and min. So like here is a relative min. That changes my graph from decreasing to increasing. Here is a relative max. It changes it from increasing to decreasing. Here is a relative min. It changes it from decreasing to increasing. So that's one of the ways to spot your decreasing, increasing behavior. Those two parts are both decreasing. So where X is less than H, it's decreasing. And then in between J and L, it's decreasing. And then it comes back up. So it's increasing from H to J. And, wait, sorry, to J. And where it's greater than L. Questions? Weird, right? But I promise you'll get the hang of it. Well, you have to do the work, and then I promise you'll get the hang of it. It won't just like jump from the iPad to your brain. But all right, so look first, okay, at concave up and concave down. Where does the, obviously the beginning is going concave, hang on, up, but where does it stop? That's what's hard. You have to see where, like if I were to continue on in this path, right, my parabola comes up like this, okay? And that's where I know to cut it. As soon as, if you carry on to J, that rate of change is slowing down, which is causing it to like level off-ish And that's why it has to cut at I. So your actual concave up cuts off at I. It would cut right there. Okay? Which means it's concave up where X is less than I. Then it changes direction. And where does that stop? M. So that's where it's concave down from I to M. Then it comes back up again the remaining time, which would be greater than M. What are the zeros? G, J, M, O, all four of them. X equals G, X equals J, X equals M, X equals O. What's the y-intercept? P. So I say y equals P. And then increasing and decreasing. So I'm going to come back in and erase my concave up, down. Identify your maximum and minimum values. So there's a relative min here, max here, min here. So I am decreasing from negative infinity up to h. I am decreasing again from k to n. So decreasing x is less than h, and k is less than x, which is less than n. And I am increasing, or the graph is increasing from h to k, and then again where n, or where x is greater than n. Questions? Okay, last one says, a ball is thrown from a hotel balcony to the ground below. The height of the ball in meters at time t seconds after it's thrown can be modeled by the function g, given by g of x equals negative 3.5 t squared plus 7.2 t plus 12.15. How high off the ground is the ball when it is thrown from the balcony? And how many seconds after the ball is thrown does it hit the ground? So let's graph this. First of all, think about the visual representation on this, right? So all those questions up to this point would be on the AP part that does not require a calculator. And then this obviously would be on the part that requires the calculator. So go ahead and go to your graphing utility, plot that. T doesn't matter, it's just an x, it doesn't matter, it's just a variable. So do negative 3.5 x squared plus 7.2 x plus 12.15. Okay, so I typed the equation into my calculator. I'm going to hit graph. I'm going to switch to my app in a second, but just so that you can see. Obviously, I don't get the full picture here. So you can choose to zoom out, or you can choose to adjust your window, okay? Let's say I just adjust my window with the Y max, and I make it like 15, and then I graph it. It's still going to get cut off, so I can adjust it again. Window, I can make the Y max 20. I can also adjust the Y min, because what is the representation of the ground in my graph?
0.
Which is what? What's that called? The x-axis. So I really don't need anything below it if I want to think about this in terms of ground, right? So I could actually adjust even my Y min to be like a -1, so it does give me the axis, but I don't really need anything below it. Does that make sense? Now I can see my graph a little bit more clearly. So if I'm thinking about the visual representation of this, where's the person on the balcony?
At the top.
Close. The tippy top, are they all the way at the max? No, where would they be? At the y-intercept, this balcony is like right there, right? That's where they're throwing it from. Does that make sense? Yes? So when it asks how high above the ground is the ball when it's thrown, what's the answer to that? 12.15. I didn't even need my graphing calculator to figure that out because that's the y-intercept, okay? So 12.15 is how high, and it'd be feet, how high off the ground the ball is thrown. Then it says how many seconds after the ball is thrown does it hit the ground? How do I know where it hits the ground? The x-axis. So how could I find that point? Find the zero. Okay. So I need to find this 0. Okay. The one before it doesn't actually happen. I didn't throw it backwards, right? It doesn't actually happen. I need that 0. So second trace 0. Go past it. And it says 3.1568073 and 0. So we're going to round this to the nearest tenth for now. It actually didn't say, okay? But 3.2 feet is, no, sorry, 3.2 feet, yes, is the x, not feet, 3.2 seconds. Okay? 0 would be the feet. Make sense? Yeah. Okay, how does it change if I add this wording? How long after it hits the maximum point does it hit the ground? Where's the maximum point? It's no longer the balcony, right? It's from here. So I need to know the horizontal distance from the maximum point to where it hits the ground. Does that make sense? So I'm going to find the maximum point. So I go to my graph, on my graphing utility, I find the maximum point. 1.0, comma 15.9. I don't need, that doesn't ask for the maximum value. If it asks for the maximum value, which obviously it could ask for things like that, it could ask for the maximum value, which would be 15.9 feet. But it's asking how long after it hits that does it hit the ground. So what am I going to do? Good. I'm going to do where it hits the ground, which was 3.2, minus the x value here, which is 1. And it would be 2.2 seconds. So these kinds of questions will ask you about a lot of stuff. It's going to obviously involve zeros. It's going to involve the maximum point. It's going to involve the y-intercept, all that stuff. You've got to be able to understand it, okay? And sometimes they go up. A lot of times it's like a ball throwing or whatever. It's going up and coming back down again. But then there are other times where it's going to go down and come back up again, okay? So, questions. There's another like weird question on your your AP classroom. What I want you to do is tonight, for sure, 100%, you have to do the PDF part of it. That's what those graph parts that we did. And then you're going to attempt the AP classroom. If you get to a question that throws you, you're not going to cry. You're not going to spend 5 hours trying to figure it out. You're going to make the attempt, okay? And if you get it wrong, it's okay. And then tomorrow when you come in, we're going to discuss it. I will say there's one that like, there's a circle and it's weird, but the video, that's why I assigned this video, that she does an actually pretty decent job of describing what it looks like on a graph. So my strong recommendation is not the 1.1 video, not the first one, but the second 1.1 video. Maybe that's a lie. It is the first one. You'll see. She talks about like a Ferris wheel or something going around. Okay, that actually to me helps with the visual representation of that question. So both the PDF and the AP classroom questions, I think there's 6 of them, are what your homework is tonight, okay? And then tomorrow we'll get some extra practice.